This is the solution to Spring 2018, problem 19. There is a ball on the end of a string, and it is being spun around horizontally. That makes this vertically. It's being spun around vertically, and that's what makes this problem more complicated, because it's experiencing not only the tension force on it, but also gravity, and the gravity depends on where it is position-wise. Luckily, we're asked to solve for the case where it's at the top. And at the top, the tension is pulling towards the center, and gravity is pulling down, and both of them are in the same direction. So if I draw a free body diagram for this, I have the mass is experiencing mg and tension. And the sum of these two forces, the net force, T plus mg, is going to be equal to the angular acceleration times the mass. This is the circular rotation condition, mv squared over r. So I plug that in, and now I'm going to solve for the tension. I'm going to subtract the mg over to this side, and I get that the tension equals mv squared over r minus g. And we're asked for the case where the tension goes to 0. And in that case, if we solve for tension equals 0, we see that that happens when v squared over r equals g. And therefore, v equals the square root of gr, which is 3.8 meters per second. Now let me just talk through what's going on here. The force on this object is the combination of mg plus t. It wants to go, like all objects, it wants to go in a straight line path, but we have a central force that is pulling it toward the center, and so it's experiencing angular acceleration. Now, the magnitude of the force necessary to get that angular acceleration is mv squared over r, period. That's how much force we need to apply to keep it going in a circular path. Now that force can either be applied by the tension of the rope or mg. And since we're at the very top of the circle, at this particular point, mg is pointing directly in the radial direction. And so if mg is large enough, this will continue to go in a circle. If it's going faster, then mg won't be large enough, and then I'll need some tension to hold this in place. If it goes slower, it's going to fall. It's not going to go in a circle. So it can't go slower than this v. And if it goes at exactly this v, then the only force holding it in circular motion at this point is mg, and the tension is 0. If it goes faster than this v, then mg will help, but the tension also has to help. There has to be a non-zero tension. And so that's the solution to the problem. The minimal v is 3.8 meters per second, and that's the velocity where the tension is 0. And that's the solution.